When valuing a project, we have to take into consideration the fact that as new information becomes available, a manager might decide to expand a project if it's going well, or downsize or abandon the project if it's not going well. And so we have to be able to capture that flexibility, that optionality into our valuation framework. And so let's see how we can do that with an example. And so in this question, we have a company that's just developed a new drug, and they're deciding whether or not to invest in manufacturing capabilities to expand their production of this new therapy. And so they're deciding between one of two options. They can either purchase new manufacturing facilities today at a cost of $1.5 billion. And if they do that, they expect that they're going to earn $200 million today. And then depending on the outcome of new pricing legislation, they're either going to earn $300 million a year thereafter or $100 million a year thereafter. And each one of these two scenarios happen with probability 50%. On the other hand, they can decide to wait a year, in which case they can purchase the manufacturing facilities 1 year from today for $1.65 billion. But now the pricing legislation is going to be resolved, and they're going to be able to decide whether or not to invest depending on the outcome of this new pricing legislation. And so the question is, which one of these two options should this company choose? And moreover, what's the NPV, or the expected NPV, of these two options? So to begin, let's consider the option to purchase the new manufacturing facilities today. In this case, the upfront cost is going to be $1.5 billion. So this is going to be equal to minus 1,500, where my units are in millions of dollars, plus they'll earn $200 million this year. And then they're either going to receive $300 million in perpetuity or $100 million in perpetuity, depending on the outcome of this new pricing legislation. And so note that these streams of cash flows can be valued using the perpetuity formula. And so we can write that the NPV is going to be equal to x1 divided by our discount rate, 10%. And so x1 is a random variable that takes on the value 300 with probability 50%, and it takes on the value 100 with probability 50%. And so because it is a random variable, we have to calculate the risk-adjusted NPV. And we calculate this by calculating the expected value of the NPV. And so we have to calculate the expected value of minus 1,500 plus 200 plus x1 over 0.1. And so minus 1,500 plus 200 is minus 1,300. And the expected value of minus 1,300 is minus 1,300. And so this is equal to minus 1,300 plus the expected value of x1 divided by 0.1. Now, what's the expected value of our profits per year after this pricing legislation occurs? And so we need to calculate the expected value of x1. And so with 50% probability, it's going to be 300. And with 50% probability, it's going to be 100. So the expected value is going to be equal to 0.5 times 300, which is 150, plus 0.5 times 100, which is 50. And so the expected value of x1 is $200 million. And so this is equal to minus 1,300 plus 200 divided by 0.1. 200 over 0.1 is 2,000. And so the RNPV, the expected NPV in this case, is plus $700 million. So that's in the case where they purchase these manufacturing facilities today. But let's see what the value is of the decision to wait 1 year and let this pricing legislation be resolved before deciding whether or not to invest in these new facilities. And so in this case, the NPV of going ahead with the project is going to be equal to, well, we're going to have an upfront cost of $1.65 billion. So minus 1650. But notice that this upfront cost is going to occur 1 year from today. So we have to discount it 1 year. And then we're going to earn these streams of cash flows in perpetuity. And so, again, this stream of cash flows can be valued using our perpetuity formula. And so this is equal to x1 divided by 0.1. But note that in this case, the company doesn't have to go ahead with the project, especially in the case where the pricing legislation decreases the profits per year from 200 million to 100 million. And so to capture this flexibility mathematically, we say that the company is going to choose one of the best option out of these two options. So max, they're going to choose the maximum of the value of either going ahead with the project or foregoing and abandoning the project. And if they abandon the project, then they aren't going to invest any additional money into this project, and moreover, they aren't going to earn any additional cash flows. And so the NPV of the decision to abandon this project is 0. And so again, x1 is a random variable that can take on the value 300 or 100 with probability 50%. And so we have to, again, calculate the risk-adjusted NPV. And so we have to take the expected value of this entire expression. So this is equal to the expected value of max. Note that 1650 divided by 1.1 is 1500. So this is minus 1500 plus x1 over 0.1 or 0. And so because this max function is a nonlinear function, it's going to have a kink in it. We can't actually bring this expected value operator inside the function. So we're going to have to take the expected value of this entire thing. And so with 50% probability, x1 is going to be equal to $300 million. So we get 0.5 times max minus 1500 plus 300 over 0.1 or 0. And notice in this case, the option to go ahead with the project and purchase these additional manufacturing capabilities is going to be equal to minus 1500 plus 3,000, 300 over 0.1. And so minus 1500 plus 3,000 is positive 1,500. And so that decision has positive NPV, and so they would go ahead with the purchase of the manufacturing facilities in that case. And so this would be equal to plus $1,500. Well, $1.5 billion. Now let's consider the case where we have the downside scenario, and the pricing legislation causes the profitability of this new drug to decrease from $200 million a year to $100 million a year. In this case, this happens with probability 50%, and we get max minus 1,500 plus 100 over our discount rate, or 0. Now, notice in this case, the option to go ahead with the project is minus 1,500 plus 1,000, which is minus 500. And so this decision would have a negative NPV. And so in this case, they would be better off with not going ahead with the expansion, but instead abandoning the project. And so here we see they would choose to abandon the project, in which case the NPV would be 0. And so we see that the expected NPV, the risk-adjusted NPV of the decision to wait 1 year before deciding whether or not to go ahead with this expansion, is equal to 0.5 times 1,500, which is equal to plus $750 million. And so we see in this case, this optionality, the option to forego the project in the case where the pricing legislation decreased the profitability of this drug, actually increased the value of the project by $50 million. And intuitively, this additional value came from the fact that we were able to mitigate our downside risk. And so by being able to avoid the situation where we've invested in this new manufacturing capabilities, in the case where the profitability is low, we were able to actually increase the total value of the project.